So yesterday we talked about the first really simplest calculation that you would have to do pertaining to a microscope. The second calculation that we need to talk about is one that refers to the field of view. And so on the left, I have a little description of what field of view is and what happens to field of view as you change magnification. On the right, I have a little formula or ratio that we'll take a look at, but I'll do an example to illustrate that. So if you could just note what field of view is and what happens to field of view as magnification changes, I'll do an example to illustrate the ratio. So if you take a look at what it says on the left first, it says that field of view is the circular area you see when you look through the ocular, lens. As magnification increases, the diameter of the field of view decreases. I'm highlighting the word diameter because we're seeing a circle, and so I'd like to specify which measurement we're actually going to take when we measure the field of view. The idea is that as magnification increases, you look at a smaller and smaller area. So I'm closer, but I see less actual space. So a good visual representation of that is actually at the bottom of the screen. I'm showing you on low power and high power what it might look like if we were looking at a picture of a playing card. On low power, see all this space on either side of the card? So I can see the whole card plus a bunch of space. And as I zoom into high power, I can still see the whole card, but now I can only see a very small amount of space on either side. So on high power, it's like I can only see that part that I circled there. So the idea is that as you change magnification and make it higher, you look at less and less and less space. That idea is something that I would definitely ask you about, probably with a picture. So I would show a picture, something like the one at the bottom of the screen, and ask you, for example, which of those two pictures shows the biggest field of view? And you would say, well, the one on the left. Which of the pictures shows the biggest magnification? Well, it's the one on the right. So if I sum this up, this is low magnification, but large field of view. On the right, this is high magnification, but small field of view. And so they're opposites, and that is a really key point. If one is big, the other one has to be small, vice versa. So based on that idea, we've got this little ratio over here. What we're saying is that if we compare the diameter of the field of view on two different powers for the microscope to the magnification on those same two powers, those things should be equal. So we're saying it's proportional. If I increase the magnification 10 times, I should decrease the field of view 10 times. So they're going up and down by the same relative amount. The D stands for diameter. The M stands for magnification. The L stands for low, the H stands for high. And what we mean by low or high is which power of the microscope are we using. So what we'll do is an example to show you how you could use this idea to calculate the field of view of a couple of different powers of the microscope. So before I show you how to calculate anything, does anyone have questions about the basic idea? As I zoom in and get better magnification, I'm looking at a smaller and smaller space. So one key point is that to do any sort of calculation, you must have at least one measured field of view. You can't calculate all of the fields of view. You have to measure at least one of them so that you have a reference. Typically, what would happen, and this is what you'll do when we go to the lab on Monday, is that you will measure the field of view on low power. The reason for that is that you can see the biggest amount of space on low power. So with a conventional tool like a ruler, you could actually measure the amount of space that you're looking at. So we're going to say, just for fun, that in these examples, we measured the field of view on low power. And so in our examples, we're going to say that we measured 4 millimeters as our field of view on low power. Now, millimeters are wonderful, but 4 millimeters really isn't very big. And when we're talking about things that are really small, like cells, we generally want to use a unit that will be the most specific. And so what we'll do is we'll take 4 millimeters and we will convert it to something that's called a micrometer. Micrometer. Now the symbol for micrometer, it looks kind of like the letter U with like a long swoopy line at the beginning. What it actually is the Greek letter mu. If you ever wanted to type it on a keyboard, if you switch to symbols and press M, you get this letter. So that's the symbol for micrometer. The difference between a millimeter and a micrometer is 1,000 times. So if I gave you a measurement in millimeters and you wanted it to be in micrometers, you would have to multiply by 1,000. That also means if I gave you micrometers and I wanted millimeters, I would divide by 1,000. And so switching between measurement units is something that you will see fairly frequently when we're dealing with stuff that has to do with microscopes and measuring cells. So far, we're saying this is going to be our measured field of view, our field of view on low power. It's the diameter of the circle that I could see under the microscope. I measured 4 millimeters, and then I converted that to micrometers so that it was more appropriate for cells. Does anyone have any questions that they'd like to ask about any of that part? So then I'll show you 2 examples. In the first example, we'll try to find out the field of view on high power. The idea that the ratio is showing us is that I put the diameters on one side and I put the magnifications on the other side. So I don't know the diameter on high power. I'll put it on the top, and I recommend that the one you're looking for always be on the top. I know the diameter on low power. It's 4,000 micrometers. So just so we know, that's the diameter on low power. And we're saying that we can make a ratio with the 2 magnifications that represent low and high power, but they have to be in the opposite order, because as magnification goes up, field of view goes down. So on the right, I would put the low power magnification on top. On our microscopes, it's 40 times. And I would put the high power magnification on the bottom. On our microscopes, 400 times. So this is magnification on low, magnification on high. So we set up a ratio. One side has the diameters, the other side has the magnifications. There's no rule about which way things have to be, except diameters both have to be on one side, magnifications both have to be on the other, and they have to be opposite. So over here, high diameter is on top, so high magnification is on the bottom on the other side. Would anybody like to ask any questions about that, how I set that up? So if the piece that I'm looking for is the diameter on high, and I have a little ratio set up, the idea is cross multiply and divide. I would do 4,000 times 40 divided by 400. So mathematically, that's how I'll find the diameter of the field of view on high. So the diameter on high power would be 400 micrometers. So that's what we would do to find the field of view on high power. And we can do a very similar calculation to find the field of view on medium power. Now, I didn't write an official formula because this is just a ratio, and I can always change the things I'm making a ratio between. In what I wrote at the top, I was comparing high and low power, but I can also compare medium and low power. So in my second example, I will try to find the diameter on medium power. I'll compare it to the diameter on low power. On the other side, I'll put the magnifications. Low power is still 40 times. And medium power on the microscopes that we have is generally 100 times. So that's magnification on low, and this is magnification on medium. So notice what I did was I replaced both of the spots where I had high power with medium power. So there isn't one official way that this formula works. It's really a concept more than a formula. If one goes up, the other one has to go down by the same amount. So when I do this calculation, I do 4,000 times 40 divided by 100. And so I would end up discovering that in this case, the diameter of the field of view on medium is 1,600 micrometers. Now I'll just pause here. Does anyone still need the screen to be up because they are writing something down? We look good here. So there's two other calculations, and these ones are a little more simple. The first of the other two is to estimate the size of a cell or any object that's in your field of view. Most of the time it will be a cell. So the instructions for estimating the size of a cell say, pick an object, in most cases a cell, that is in your field of view. So I'm going to imagine that I picked that cell, the first one that I colored. And then the second point asks you to estimate, and I really do mean estimate. There might be more than one way to answer a question correctly when estimating is what you're using. But you're going to estimate how many times that object will fit across the field of view. So I would estimate, because I filled it in, that object would fit 5 times across the field of view. Another way of saying this would be to say that that cell took up 1/5 of the field of view. And then we do the actual math where we divide the field of view diameter by that number, the number that you just figured out in step number 2. So let's say for fun, in this example, I was on, let's say I was on high power. If I was on high power, and we'll use the numbers that we just calculated. So we just calculated that the field of view on high power in our little examples was 400 micrometers. And we counted that 5 objects fit across the field of view. So that means that each of those cells has a size, and by size, we generally mean the width, like going from left to right, because that's what we're measuring when we're measuring diameter, is the distance across the circle like that. We could measure the height of the cells as well. Keep in mind that diameter can be anywhere on the circle. As long as you're going from one side completely to the other, a circle has the same diameter all the way around. But most of the time, we're going for the width, unless we say otherwise. So what I would be saying is each of those cells is 80 micrometers wide. So this is something that you would have to do in the lab, but also that I would ask you about in a test situation, because I could make a sketch much like the one that's up there and give you some values to calculate with. So the last step of calculations that you would have to do with microscopes is to calculate the magnification of a drawing. Sometimes when we're talking about magnification of a drawing, we use the word scale. And you would see this word used on maps a lot of the time, because we're trying to say, with reference to what it actually is, how big is this picture? Maps are always smaller than reality. Your microscope drawings will always be bigger than what the thing you were actually observing was. So when you want to find the scale or the magnification of the picture or the drawing that you've made, you will use a ruler. So it would be very realistic, both in the lab and on a test or on a quiz, for me to ask you to actually measure a drawing and figure out its scale. So you would take your ruler, like I will do here, and measure the diameter of your field of view, or just measure one of the cells. In my picture, the actual size and the drawing size are what I'm looking for. My drawing size here is about 5 centimeters. The actual size of my cell is 80 micrometers. And so I'm comparing what I measured with my ruler with what I just calculated, how big that cell actually is. Now, I could just divide those and be done, except that would be a really bad calculation because I don't have the same unit. And so this is a good example where you need to change units. Now, they both have to be the same unit, but there's no rule that says which unit they actually have to be. And you can do whatever you prefer, but I'm going to make a suggestion. I think that most of you are aware that there are 10 millimeters in a centimeter. And if you forget, you can just look at your ruler and count. That's something that people are usually familiar with. People, now that I've told you, are also usually familiar with the idea that there are 1,000, whoops, I need one more zero there. let's just fix that, that there are 1,000 micrometers in a millimeter. So I'm recommending that you use millimeters. Now what does that mean? That means that when you measure your drawing, why not measure it in millimeters right from the get-go? Then you won't have to convert the unit. Centimeters is probably the unit that you would gravitate to because it's bigger and it's marked on the ruler. But I want to have the same unit for both of my numbers in the calculation, so millimeters makes a little bit more sense. In this case, then my magnification of my drawing would be 50 millimeters divided by 0.080 millimeters. So you should get a big number as your answer. If you ever get 0 point something as your scale, you had the numbers in the wrong order. So this should always be a relatively large number. So when I do 50 divided by 0.08, I get 625. Now, am I going to put a unit? Well, millimeters and millimeters cancel each other out. So generally when we're writing scale, you don't have to write an official unit, but we do tend to write this. The scale of something is 625 to 1. That means for every 1 unit in real life, my picture is 625 times the size of that.